Hello everyone, and welcome to the first TS video. In this video, my aim is to explain why do we have all these numbers. Is it possible to come up with some kind of structure, some reason for why we have them, in some way organize them, and talk about areas of use of these numbers. To begin, let me show you an example of all these different kinds of numbers that I'm talking about. So here on the right side, I have an example of some of these numbers, a sampling of these numbers. And if you think about it, all these numbers like 4, there is 0, there is decimals like 0.5, fractions like 1/2, negative numbers, -4, and then there are these more exotic kinds of numbers like √2, pi. Sometimes we use scientific notation and write -1.4 times 10 to the power of -2 as an example. So the idea is, right now it seems like it's just a jumble of numbers, and there is no really coherence. There is no explanation as to why is it that we need to work with all these numbers. If you think about it as an example, 1/2 and 0.5 are pretty much the same. And the question is, why is it that we even bother with fractions if we can work with decimals? Same thing with √2. You can write it down approximately as 1.41 and so on. Pi 3.14159265 and so on. And the question is, why do we even bother with them? Why not just use decimals? Okay, so it's about number systems. And to begin, I would like to remind you that in this series, we always follow the increasing level of complexity of the kinds of problems that we solve. And of course, when we talk about the increasing level of complexity of our problem-solving needs, we're talking about, at its simplest, there are problems that require that we add. There are problems that require that we subtract, multiply, divide, and so on. And we're going to follow this order. We're going to start with addition and see if all of our needs are met. And then we move to subtraction, take a look at our needs. And at any point, if we find that we need something and some new idea in math, then we will introduce it if it helps us in our problem-solving needs. All right, so we begin with natural numbers. These are the simplest kinds of numbers that we have. And these numbers are 0, 1, 2, 3, 4, and so on. The 3 dots on the right side is read as and so on, implying that the same pattern continues. We use capital letter N, but a fancy version of it to refer to the set of natural numbers. Now, when it comes to our problem-solving needs, starting with the simplest kinds of problems that we solve, which are those that require that we add. One question that we should answer right from the beginning, before we even take up the first word problem, is, will we be able to add these numbers, in the sense that if there is a word problem that requires that we add 2 of these numbers, will I always be able to do that? And by that we mean, will I always get a number? If I pick any 2 numbers from n and add them, will the result be a number? Now, keep in mind that numbers in n are the only numbers that we saw so far. There is nothing right now other than 0, 1, 2, 3, 4, and so on. In other words, we don't have the decimals, we don't have fractions, we don't have negative numbers, nothing like that. It's just 0, 1, 2, 3, 4. And so it does happen to be the case that if we take any 2 numbers from n and add them, then the result will be in n. So if I add, let's say, 1 and 2, I get 3. And 3 is a number in n. So I can add 1 and 2 and write the answer down. I can add, let's say, 2 and 4. I can add 3 and 4. And let's say again, if I add 3 and 4, I'll end up with 7, which happens to be a number in n. So when that happens, when I pick 2 numbers from n, add them, and guaranteed that the result will be in n, then we say that n is closed under addition. So once again, the phrase n is closed under addition means if you pick any two numbers from n and add them, the result will be a number in n. So we will not have any problems if we need to add the numbers in n. We can always do so. We are going to now move on to the next most complex kinds of problems that we solve. And these are the ones that require that we subtract. And when it comes to subtraction, we run into a problem. Take a look at this word problem. The temperature was 3 degrees Celsius this morning. It went down by 5 degrees Celsius. What is the temperature now? And to solve this problem, we have to do 3 minus 5 in that order. And the problem is that, keep in mind, these are the only numbers that we have so far. I will not be able to solve this problem. I will not be able to write something in place of the question mark because none of the numbers in n are able to answer this question. 3 minus 5 equals what? And of course, the question comes up as to, do I even care about 3 minus 5? And as you can see in the word problem here, yes, I do. I would like to be able to answer this question. We do expect that there is an answer to this question. And this led us to invent integers. And these are numbers, well, basically, they are the naturals as well as the negatives of the positive naturals. So the pattern continues on both ends, and we have numbers like going forward, we have numbers like 0, 1, 2, 3, 4, and so on. Going backward, we have -1, -2, -3, and so on. And now I can write the answer to the problem above as 3 minus 5 equals -2. Z is closed under both addition and subtraction. So you can take any two numbers in Z and add them, and guaranteed the answer will be a number in n. You can also take any two numbers in Z and subtract them, and the answer will be a number in Z. Keep in mind that for closure to hold, we should be able to add any two numbers, not just two specific pairs of numbers, but any two numbers, and the result will be in the same set, in Z. So far, we've dealt with all of our needs for addition and subtraction, and these correspond to the first two simplest kinds of problems that we solve. The next most complex kinds of problems that we solve require that we multiply. And it so happens that n and z are both closed under multiplication. In fact, one of the things that we find is that as far as closure goes, we don't have any problems with forward operations, with addition, multiplication, later on exponents, and so on. The sets that we invent are always closed under these operations. What we have problem with, as you already noticed with subtraction, is with backward operations. So we did have closure with respect to addition in n, but we didn't have closure with respect to subtraction. We do have closure with respect to multiplication in both n and z, but we don't have closure with respect to division. So you see addition, multiplication, closure guaranteed for both n and z. Subtraction, not for n, but it is closed. Z is closed under subtraction. And we notice that now we're going to have a problem with division. And let me emphasize the point that I was just talking about, that for forward operations, addition, multiplication, and so on, we have no problem. All of our sets will be closed under addition. All of our sets will be closed under multiplication, and so on. With backward operations, we do have a bit of a problem. All right, let's move on to the next problem. And this problem says that we want to divide 2 pizzas between 3 people. How much pizza does each person get? And to solve this problem, we have to divide 2 by 3. And at present, we don't have fractions yet. And the horizontal line should be interpreted as division. So we're talking about 2 things divided into 3 parts. And I will not be able to write the answer to that problem given that the only numbers that I know are the numbers in n and z over here. Keep in mind, these are the only numbers that we know so far. And so we will not be able to write the result of two things divided into three parts. And this led to the invention of rational numbers. In fact, rational numbers, now this looks a bit cryptic, but I'm going to decode it in a minute. But basically, we're talking about new numbers that have the form of a rational number, the form of a, if you like, fraction, although they can be positive or negative. So let's decode this for a minute. We have Q, which is the set of rational numbers, is the set of numbers like P over Q, such that the vertical line is read as such that P, which is the top number, and Q, which is the bottom number, belong to Z. In other words, we are saying that the top and the bottom are integers. Now, why is it that we have that kind of restriction? Because numbers in Z are the only numbers that we know so far. So what else would we put on top and the bottom? So that's why the top and the bottom are integers. And an additional condition that the bottom number, Q, cannot be 0. And we need to talk about that a bit as well. Here's an example of why division by 0 is excluded. Let's take a look at an ordinary division first. 14 divided by 2 is 7. And of course, we can check that by multiplying 2 by 7, and we should get 14 back. So keep in mind that the check works by multiplying along the diagonal, 2 times 7, and we should get the top number, 14. Now, let's take a look at 0 divided by 0. And if we wanted to check the answer to this problem, we would, of course, have to make sure that 0 times the question mark, multiplying diagonally, would give me the top number, 0. And if you take a look at the possibilities for the question mark, you would soon convince yourself that it can be any number. I can put 1 in place of the question mark here, and the check will work. I can put 0. I can put -8. I can put anything that I want, and it will always work. So the answer to 0 divided by 0 is that it can equal to any number, not one specific value, but any number is an answer to this problem. And so we call these kinds of expressions, which can equal to any number, we call them indeterminate. So indeterminate expressions are expressions whose answer can be any number. Now, if the top number is not 0 and I try to divide by 0, I run into a different kind of a problem. Now, if I try to check, I would have to make sure that 0 times the question mark is 4, and that's impossible. So in this case, there is no answer to this problem. No matter what you replace the question mark with, you will never end up with 4. And these kinds of expressions that have no answer to them, we call them undefined, which means they are meaningless, basically. If you divide 4 by 0, you're not going to get any number, because nothing will work in terms of when you check it, you're not going to get 4. So these are the complexities that we run into when we try to divide by 0. If it's 0 divided by 0, it's indeterminate, which means the answer can be any number. If it's some non-zero number divided by 0, then it's undefined, which means that there are no answers to it. And because of these complexities, we exclude division by 0. In one case, it's not even a number, so it cannot be a rational number. And in the other case, it could be any number, numbers that are not rational. And so we also exclude that scenario. And basically, both of them can be excluded if we make sure that we don't divide by 0. The bottom number cannot be 0. All right, now we can write the answer to our division. 2 things divided into 3 parts is equal to 2/3 of 1. Now differentiate between what the left says and what the right says. On the left side, we have 2 things divided into 3 parts. So 2 pies divided into 3 parts. The shaded part is 1. These 2 pieces together make 1. and this piece over here is 1. So 2 pies have been divided into 3 parts, and one piece will have the size of the shaded part. Now on the right side, we're talking about 2/3 of 1, and that's this pie. We take 1 pie, divide it into 3 parts, and take 2 of them. And as you can see, if I divide 2 things into 3 parts, which is this, I'll end up with 2/3, which is this. And this can always be done. So although it seems like we are saying something that's obvious, keep in mind that the reading on the left is different from the reading on the right. On the left, we're talking about what needs to be done. 2 things need to be divided into 3 parts. On the right side, we're talking about the size of the result, which is 2/3 of 1. All right, let's now take a look at the set of numbers that we have so far. So far, the numbers that we have are n, z, which also includes n, as you can see, and q. And by the way, q also includes the numbers in both n and z. For example, -3 can be written as -3/1, which then will have the form of a rational number. So rational numbers already include all the numbers in z, which already includes all the numbers in n. Okay, so what we have so far now is that the numbers that we have come up with in q, we can add them, subtract them, multiply them, and so long as we don't divide by 0, we can also divide them. And the answer will always be a number in the sense that one of these numbers, of course, because that's all that we have so far. And we can always write the answer down. And so q is closed under addition, subtraction, multiplication, and division, other than division by 0. That should have been an A. All right, no problem. Now, the next problem that we're going to look at is a problem whose solution cannot be written down using any of these numbers that we have. Okay, the next problem is a right-angled triangle has a side length of 1. Calculate the length of the hypotenuse. Now, to show you what that means, let's take a look at this diagram. This is a right-angled triangle. The right angle is over here, and we refer to the long side as the hypotenuse. And most people know, you might have forgotten, but I'm sure at some point you've seen the Pythagorean theorem, which says that the square of the hypotenuse, the long side, is equal to the sum of the squares of the short sides. So you square A, you square B, and add them, and you get the square of C. Now, we would like to apply this problem to a specific triangle which has a side length of 1. So A is 1, B is 1, and we want to find C. And going by the Pythagorean theorem, we have C to the power of 2 is equal to 1 to the power of 2 plus 1 to the power of 2. That's A squared plus B squared. So C squared becomes 1 plus 1, which is 2. And therefore C will be root 2. Now technically it would be positive or negative root 2, but in this case we're talking about length, which cannot be negative. So I only retain the positive answer. So the length that I'm seeking can be obtained if we find the square root of 2. Now, they tried to see which of the numbers that we have, which of these numbers up to q, let me go back actually to the previous diagram. There we go. So they tried to see which of these fractions corresponds to the square root of 2, only to find out that none of them do. In fact, it can be proven that the square root of 2 is not equal to any rational number. I have given a proof of this in the appendix of my textbook, Style in Technical Math. The proof is somewhat long, so I'm not going to reproduce it here. I'm sure you can also find it online. But it can be proven that there is no fraction, positive or negative fraction, that corresponds to the square root of 2. If you want to prove this on your own and give it a try, try 4 cases where the top and the bottom, keep in mind they come from Z. where the top and the bottom are both even. Top is even, bottom is odd. Top is odd, bottom is even, and they're both odd. And you'll find that in all these four possible cases, you're going to run into a contradiction, which means that there is no fraction that corresponds to the square root of 2. And so we have come across a new size, a value whose size cannot be written down using any of the numbers that we have. And this led people to the invention of new numbers, and these are called real numbers. I'm not going to define R, other than noting that the capital letter R, or the fancy version of it, is used to refer to real numbers. Real numbers are somewhat tough to define. And what we need to know, though, is that if we come across any numbers that cannot be written down as a rational number, then these are numbers that belong to R. They don't belong to Q, Z, or N. Amongst other numbers that are not rational is the number pi. Basically, any root that cannot be worked out is irrational. And there are other ones like log to the base 2 of 3 and so on, the golden ratio and so on. Okay, so now we have R, and what we do is following the approach that we had with rational numbers, where on the left side we were talking about the need to do something. We need to divide two things into three parts. And on the right side, we talk about the answer to it, which is 2/3. We're going to do the same here. On the left side, we're talking about the need to take the square root of 2. And on the right side, we write down the answer, which is the square root of 2. And so now we have new numbers like root 2, pi, and so on. And these ones belong to R. Let's take a look at all the sets that we have so far now. There we are. So N, Z, which extends N, includes N. Q includes Z and extends it. And R, by the way, R is not just the new sets of numbers, the new numbers that we come across, like root 2 or pi. It does include everything in Q in addition to all the new numbers that we may come across. All right, so what we have now is that R is closed under addition, subtraction, multiplication, division, other than division by 0, and also it's closed under other operations, but like taking a square root, other than any inherent limitations on these operations. Okay, so again, with forward operations, we have no problems. All of our sets N, Z, Q, R are closed under addition, subtraction, addition, multiplication, exponentiation, and so on. But with backward operations, we always had trouble. For subtraction, we did not have closure with N, and so we introduced Z. With division, we had to introduce Q. And with all other ones, we introduced R. All right, it's also important to keep in mind that these sets extend the ones that come before them. So N, for example, which is the set that extends to this point, includes numbers like 3, 10, 0, and so on. And Z starts from the very beginning. It doesn't include only the extension. It includes everything from the beginning. So Z includes 3, 10, 183, 0, but it also includes -1, -412, -17, and so on. Q extends Z. So Q already includes everything that was in N, everything that's in Z, and now it adds on the rationals like 1/2 and 3/8, which we couldn't write down using the notation in N or Z. And R extends Q, so it includes everything from the beginning all the way to here. And therefore, a number like 10 is a natural number. It's also an integer, and it is a rational number, and it is a real number. -1 is not natural, but it's an integer, and it's also in Q, and it's also in R. 1/2 is not natural, and it's not an integer, but it's in Q and it's in R. Okay, so that's the relationship between the numbers that we have defined so far. Okay, the next item of discussion is on notation. And when it comes to notation, let me just give you an overview of what we're going to be talking about. As far as notation goes, we'll find that there are two of them. One is the formal notation, and the other one is base 10 notations. The formal notation is what we just talked about, the notation that we use to write the numbers in N, Z, Q, and R. Base 10 notations are those notations that use decimals, like decimals or scientific notation, which is a sort of modified version of the decimal notation. Now, we have both sets of notation for a reason, because each set has pros and cons, and each pros and cons are complementary. So the strengths or the weaknesses of the formal notation are basically the strengths of base 10 notations, and vice versa. What's so special about the formal notation, and one reason we cannot really get rid of them and only use decimals and scientific notation, is that they are exact and they are descriptive, and I will be talking about what that means. But if you take a look over here, you notice that with base 10 notations we don't have that. They're not always exact, or even if you could in some way argue that they are exact, they are almost impossible to work with unless you round them, and they're not as descriptive. But the weakness of the formal notation is that it's a complicated kind of notation to use. If you think about it, with the introduction of Z, we now have to come up with algorithms that teach us how to add these numbers, negative numbers, and how to subtract them, how to multiply them, divide them. When we introduce rationals, which are fraction-like, they're actually positive and negative fractions. Now we have to talk about algorithms for adding them, subtracting them, multiplying them, dividing them, and so on. And then in R, we have to talk about algorithms that allow us to add roots, another set that would allow us to deal with logarithms, and so on. And this is pretty complicated. Base 10 notations are much simpler. And the applications of these with formal notation, we use them in the expression of scientific theories, because when we talk theory, we have to be exact. There is absolutely no rounding allowed in theory. And we have to be descriptive. What we write must be very clear. We should be able to tell at a glance what it is that we are talking about. Whereas base 10 notations are used in the expression of applications of scientific theory, where we make actual measurements. And when we measure things, unless you count directly, the value that you get is approximate. There is no way any of us can ever measure the length of a table absolutely exactly. You would never ever know that you're not off by just a tiny bit. It could be off by a hair. And even if it looks like that the end of the table falls right on a division on the ruler, you can never be sure again that it's not off by a hair. And so it's impossible. You can zoom in even, and if you zoom in too much, by the way, the smooth edge will become sort of like going back, and like you can't really tell where the end of the table is if you zoom in a lot. And so the question becomes, where is that end anyway? So because it's impossible for us to be absolutely exact when we measure things other than direct counting, then why bother with this formal notation? Let's go with the simpler decimal notation or scientific notation. And so that's where we use base 10 notations. And as you can see, we are stuck with both of these notations, and that's why we have all of them. Now let's expand a bit more on what we mean by exactness and descriptiveness. Okay, so exactness Here is formal notation and decimal notation numbers that are written using the formal notation. As you can see, there is 3/4, there is 2/3, square root of 2, and pi. And here we have the decimal notation. 1, of course, can be written as 1, -2 is -2, 3/4, 0.75, 2/3 is 0 point repeating digits of 6, and then we have the square root of 2, which is 1.414 and then more digits, and pi 3.141 and then more digits. The 3 dots indicate that the value will never end. You will forever have digits, more and more digits coming. Now in the case of numbers like 2/3, there will be a repeating pattern. But if you go to numbers that are not rational, like square root of 2 or pi, you'll find that not only do the digits never end, no part of this will ever repeat. Same thing with pi. And one question that comes up is, how do we work with these numbers? Like suppose I want to multiply root 2 by pi. How do I multiply these when I don't even know what comes after? You might say, well, let's round this to 1.41 and this one to 3.14. That's usually what we do. But keep in mind, then that's an approximation. What if we have to be exact? Then you can see that the decimal notation becomes pretty much useless, whereas the formal notation is exact. And so that's why we use them in the expression of scientific theories, because in theory there is no approximation. It's assumed that theoretical equations, formulas, conclusions that are based on theory are absolutely exact. There is no approximation to them. Now, let me give you an example of what I'm talking about here, as to what it is that we call exact. Why is it that theory is exact? Let's take a look at this problem where we want to come up with a formula for the area of a triangle. Here I have a rectangle with a length of b and a width of h, and of course the area is length times width, which in this case it's bh. Now take a look at this parallelogram where the base has the same length as the length of the rectangle, and the height of the parallelogram is the same as the width of the rectangle. Now these two shapes have the same area. You can see that by cutting this triangle along the dotted line and then move it over to here, and then you'll end up with a rectangle. So the areas of these two shapes are the same, and if this one is BH, then this one is also BH, base times the height. And the triangle is exactly half of this. You see, if you cut the parallelogram along this diagonal, you'll end up with that triangle. And so there are two of these triangles in the parallelogram. And so if the area of the parallelogram is BH, the area of the triangle will be half of it, which is 1/2 BH. Now you notice that this is exactly 1/2 of the area. The area of the triangle is exactly half of the area of the parallelogram. We're not talking about it being close to half or approximately half. In fact, we made no measurements. We just talked about it. We reasoned our way through it. This is what we call theory, and this is exact. And that's what we mean by theory is exact. And therefore, that's why we use the formal notation here. You see, no one, no mathematician, no physicist, no scientist worthy of their degrees would start this formula with 0.5 BH. Right? You always see the formal notation being used because it's exact, and therefore that's what we want in theory, and that's what we use. Okay, so that's about exactness. Now the next thing we need to talk about is about descriptiveness, and for this I'm going to give you I'll give you again a table where on the left side I have formal notation 3/8, which has a decimal equivalent of 0.125, and 2 pi, which is 6.283, and so on. And as you can see, the formal notation is much more descriptive. It takes almost a fraction of a second for me to realize what we're talking about when we say 3/8. Take something, divide into 8 parts, take 3 parts. There is no way I can look at 0.125 and have that clarity of understanding. And 2 pi, same things. I know that I'm trying to find twice the value of this special number called pi. And I know that pi is playing a special role in my talk. Here, I don't see that. It looks like randomness, 6.283. I don't see there is pi in there, right? This is what we mean by descriptiveness. And because when we talk theory, we are communicating, and we would like to be as descriptive, as clear as possible. Again, the formal notation is our obvious choice, and the decimal notation is not that good. All right. Now, when I measure the length of a table, I can't be exact. First of all, I cannot be exact. And second, I don't need to be descriptive. Who cares about the length of a particular table, right? There is a reason we have pi, because it has to do with the intrinsic properties of a circle. But the length of a table is just the length of a table. It could be off by 0.001, and probably no one would even care. And so we don't need to be descriptive about it. We don't need for people to know that 0.125 is always the length of this table. And so because we cannot be exact when we measure things, and we don't have to be descriptive, why not switch to the use of the decimal notation when we make measurements? Okay, let's now take a look at the next image. Oh yeah, the areas of use. So as I said, in the expression of theoretical formulas, you see the use of the formal notation all the time. The area of a triangle is half times the base times the height. You see the use of the formal notation. The circumference of a circle is 2 times pi times r. Again, you notice the use of the formal notation. We've got peak voltage is equal to the square root of the root mean square voltage. And again, you notice the use of the formal notation. When it comes to the expression of measured values, though, we use decimals. So if I'm trying to work out the area of an actual triangle, which has, let's say, a base of 4.7 centimeters and a height of 1.3 centimeters, then I switch to the use of decimals. Here's another one. Circumference is 2 times, now you see I replaced the value, I replaced pi with its approximate decimal equivalent of 3.14. And the radius in this case is 1.8. And here's one for the peak voltage. Right, you see that root 2 has now been replaced with 1.4142. Of course, how many digits you keep depends on how accurate you want the result to be. So if I'm working on a problem, the area of a triangle is 13.76 square centimeters. Calculate the height of the triangle if its base measures 4.3 centimeters. Then I start with theory. I say that I already know that the area of a triangle is half times the base times the height. And I would like to find the height. That's what it says I should find. So I'll switch sides and then solve for h to end up with 2a divided by b. Now you see, up until now, it's all theoretical discussions. And therefore, I'm using the formal notation. There is no decimals here. Now, I'm going to replace the values with the measured values of 13.76 and 4.3. And you notice the decimals coming. And we finish the problem, again using the decimal notation. And we get the height is 6.4 centimeters. Okay, sorry about that. Yeah, and then a couple of things that I want to say before we close this. One is on the use of the notation that we have. The formal notation is actually pretty interesting if you think about it. Here are some operations that we want to be able to do. We want to find the sum of 70 and 2, do the subtraction 3 minus 5, divide 4 by 6, and find the fourth root of 9. And also be able to work with numbers like pi, find pi. For some of these, we have reduced operations, and for some we don't. So of course, if we are adding 70 and 2, we write the result as 72. However, it should be noted that this is really a shorthand for that. Like if somebody looks at 72, what comes to their mind is that they have to add 70 things and 2 things and take the total as the answer. So we still do some kind of work in our head. We add 70 and 2, and then we understand what the totality is that we are talking about. Same thing here, 3 minus 5, and the reduced operation is 0 minus 2. You can always get the reduced operation if you reduce the subtraction much the same way as you reduce the division, except with subtraction, you subtract equal quantities from both operands. So I can subtract 3 from both of these operands, and if I do 3 minus 3, I get 0. If I do 5 minus 3, I get 2. And then, because we always subtract the first operand from both, we always end up with 0 at the beginning, and then we can drop it and write negative 2. However, negative 2 comes from 0 minus 2, and with the 0 dropped. And 0 minus 2 comes from something like 3 minus 5, maybe 4 minus 6, and so on. But the key is that by dropping the 0, we make it appear as if we are talking about the value that we arrive at. So negative 2 is the result of the reduced operation 0 minus 2. This is incidentally why the negative sign is identical to the subtraction sign. Mathematicians, I would say, are pretty careful people, and they would use different notations, like maybe use a star here to refer to a negative number. But because of this association between the negative and the subtraction, which comes from dropping the 0, we kept the same kind of notation. You also notice that in order for us to ensure closure with respect to subtraction, we use this sign for that operation. That's pretty neat. For division, 4 things divided into 6 parts. The reduced operation is 2 things divided into 3 parts, and the answer to it is 2/3 of 1. Now in this case, unlike subtraction, we are unable to come up with 2 different notations to write the operation itself and the result of that operation. In the case of subtraction, we were lucky because the first operand was always 0, and we could therefore drop it and make it appear as if we have now a number. But with division, we cannot do that because the top number can end up being anything, and therefore we have to keep both the top and the bottom, and that makes the 2 notations, the operation and the result of that operation, to look identical. So you should train yourselves to see a notation like this in 2 different ways. One is 2 things divided into 3 parts. The other is the result of that, which is 2/3. Same thing with other notations like roots. If you're trying to find the 4th root of 9, you can reduce that to the 2nd root of 3. And again, we're going to use the same notation to represent the result with. So the use of the operation to indicate the result of that operation is pretty much what formal notation is about. If you're subtracting, the subtraction notation is used to refer to the result of that subtraction. If you're dividing, the division notation is used to refer to the result of the division. if you're taking roots, the root notation is used to refer to the result of that operation. So that's the formal notation. Now, base 10 notations have a different kind of structure. They start with either a positive or a negative sign, and then they have these things called places, and each of these places have certain values with a decimal point somewhere. So for example, these are in the ones, this one is in the tens, this one is in the hundreds. On the right side we have tenths, hundredths, thousandths, and so on. And base 10 notations try to bring some uniformity to this complicated formal notation. And because base 10 notations use place values to deal with the size of a number, the notation is unable to deal with positives and negatives, and therefore it follows the lead, I would say, of the formal notation in using the negative sign to refer to negative values. Okay, so we have this diagram then: formal notation, base 10 notations. Formal notation is exact and descriptive, and it's used in the expression of scientific theories which require that we be exact, absolutely exact, not even the tiniest of roundings. And we have to be descriptive, so we can quickly look and say, we're talking about 3/8. 0.125 doesn't have that kind of an impact. But the formal notation is complicated. Base 10 notations are not always exact, not as descriptive, but they are simpler. And when we make measurements, such as here, where we measured the area to be 13.76 and so on, we switch to the use of base 10 notations. Much simpler to work with, and there is no need to be exact or descriptive when we make measurements. Okay, everyone, this brings us to the end of this video, and I will be gone in 3, 2, 1. Bye bye.